Hey, Farouk here. I hope you're doing well today and you're staying on top of your FE exam prep. Remember, you do not have to know it all to pass this FE exam. You do not have to know it all to tackle this exam with confidence. Really know your basics, know the fundamentals, and do not fixate on certain problems that are, let's say, curveball problems, problems that are not foundational or fundamental. Don't fixate and try to memorize solutions. Don't fixate on specific problems. Stay well-rounded, stay flexible, know the basics, and remember you do not have to know it all to pass this exam. If you're comfortable with the basics, you're going to absolutely crush this exam. Today we got a hard dynamics conceptual question that does not involve numbers. No numbers. So we're given an inclined plane, we're given a block, and it's accelerating down on that classic inclined plane. And we want to select the correct answer or arrive at the correct conclusion based on the specific problem statement. Let's read it slow. Let's read it together so we know we have a block is sliding down an inclined plane shown below. The coefficient of kinetic friction between the block and the plane is mu kinetic, mu kinetic, coefficient of kinetic friction. As the angle of the incline theta increases, which of the following statements is true? Now, going down, A, B, C, or D, it's only one answer in this one. Acceleration of the block increases and the magnitude of the friction force decreases. Acceleration of the block increases, but the magnitude of the normal force and the magnitude of the friction force remain the same. Acceleration of the block decreases, but the coefficient of kinetic friction remains the same. Acceleration of the block and the magnitude of the friction force remain the same. What would you pick? As the angle of the incline increases, which of the following is true? As this angle goes up, what would you conclude? So I want you to pause the video and see if somehow you can answer this. You can either use formulas or maybe you can think about this just logically or physically based on the physical condition when you increase that incline angle. Give it a shot and come back and check your work with mine. Now, so we will answer this specifically using a technique that you can apply to other questions similar to this. Notice in this one, it's an inclined plane. You can apply this to beams, trusses, or any question really that forces you to use this kind of judgment to arrive at that conclusion. It doesn't use numbers, but we can still use formulas to get the answer. So that's one technique. But before all of that, we can also think about this logically or physically. So the way I'm going to do that with you is to look at this physical example. So what we have is a beam here, and we know it's going to be allowed to rotate about this end here. So this is a hinge and it's allowed to rotate. And this helps us visualize the inclined angle. So notice this is an angle here of 0 degrees. I increase this, let's say 10 degrees, 20 degrees, 30, and so on. And this would be what? Right here is 90 degrees when we have it just straight. So we know what we will now introduce is the block. So we introduce our block here. And we can think about this. Notice that in this case, even if I increase the angle, nothing's happening because we're still in static friction. So the block doesn't have a component, a weight component along the parallel that's large enough to break the static friction force. So we're actually still in the static mode. But this one is a kinetic. Things are moving. Dynamics. It's accelerating. So we have to actually break that critical angle where the weight component along the parallel, this way along the parallel, is strong enough to break the static friction force to force this to move or accelerate. Then we're in kinetic friction. And we're in kinetic friction, things are moving, and what governs is the kinetic friction force. So we're still in static. So what I'm going to do is incline this to a specific critical angle to watch this move, to watch it accelerate. And that will help us answer this. So let's say I move it like this. And this is the specific incline angle here with respect to the horizontal. It's a large angle, but that will surely make this accelerate. So if I let go of this, watch the acceleration and see if it's, let's call it fast or accelerates a lot. So if I let go, we have this. So we have that case when we did that. So you watch that, and that was at a specific angle. Now, what do you think is going to happen when you increase the angle more? When we increase that incline angle, is it going to accelerate less or more? Logically, I bet you know what the answer is. If you increase the angle, this would accelerate more. As we will see here, it does accelerate more. So again, this is the acceleration when it's like at a low angle, the first angle that we have. So I let go and accelerates like that. Now, if I increase this angle, let's see how this accelerates. It's going to be a lot more. So that's how we can think about this physically. And that's one way that we can do this. But we're going to also talk about this and solve this using formulas. So based on that physical relationship, you can probably answer this, or you might eliminate, let's say, 2 answer choices. Let's solve this using formulas. The first thing I'm going to do is, I know I'm dealing with dynamics. I'm going to draw the free body diagram. So let's draw that free body diagram of this, and I'll just do it on the block. So we have a mass here. So this has a weight, and the weight goes directly towards the center of the earth. So I'm going to denote it like that. And that would be my weight, total component of the weight, W. And we know weight is mass times gravity. Remember that. Now, we know that the weight here is not good enough because I have to break it up into the components along the parallel and the perpendicular. Always for inclined planes. We talk about this in another video. I'll link that below. So what will happen is this. We have the components. This is the x prime direction, and this is the y prime direction. This is positive. This is positive. Going this way is positive. Going that way, up perpendicular to the incline, will be positive. So that weight component, I break it down into a component that's going to go down this way. So this is the right way to break down that component. This is wx prime. And we have a weight component that goes this way. This is wy prime. Now, with that said, I know I need to denote this angle theta. That's very important because the theta angle allows us to break up the components or actually get the values for those. So this is angle theta, so it must be here. In this case, it's always with the y component for these classic inclined plane problems. Theta should be there. Don't put it there. That would be a big mistake. With that said, we know we can denote the normal force. There's always that normal force, right? Perpendicular. Now, are we missing something? What's something I need to draw? Make sure I draw. The problem says kinetic friction between the block and the plane, and it has mu kinetic. There's kinetic friction. Now the acceleration is going this way, so the kinetic force, friction force, is going to go this way, kinetic. And that friction force kinetic, let's write that on the side, is going to be mu kinetic, the coefficient of kinetic friction, times the normal force. And that's always the formula in the state of dynamics. Things are moving, so it should go up opposing the direction of motion or acceleration down. And that looks like a complete free body diagram. I denoted everything. Then what I'm going to do is use the formulas and use the equations of motion, Newton's second law. We're going to do that in the y direction or the y prime direction, and we're going to do that in the x prime direction. Let's start with the y prime direction. So we're going to say sum of the forces in the y prime direction must equal to mass times acceleration in the y prime direction. And this is a vector. And we're going to say going this way is positive. Now, if you look at this block, does it accelerate in the y prime direction? Perpendicular this way. Does it accelerate? No. And you should say no, it doesn't, because it only moves in this direction. So here, all of this is 0. So what this really becomes is sum of the forces in the y prime equals to 0. Going this way is positive. Now let's put the net forces. Sum of the net forces in the y prime direction. It's going to be wy prime going this way. So it opposes this direction. So that should be negative. Negative wy prime. And then we do plus the normal force. And this equals to 0. So this ultimately tells me, as you see, the normal force equals to wy prime. So let's denote that here. Normal force will equal to the wy prime. And then what is wy prime in terms of w? That will be helpful as we continue. Wy prime in terms of w is going to be w. The angles here, it's going to be w cosine of the angle theta. And we're going to adjust the angle theta based on this problem as it increases. So let's define it in terms of the angle theta. That's very important as we continue. So that wy prime is w cosine of theta. W is here, cosine of theta. So that's going to be in the y prime direction. Now we will do the same process in the x prime direction. So what we will do is say sum of the forces in the x prime direction equals to the mass times acceleration in the x prime direction. And going this way will be positive. Going this way is positive. With that said, let's do some of the net forces. We have the force of friction. It goes up, so it should be positive. Positive force of friction, kinetic. Then I have the negative Wx prime, and that equals to the mass times acceleration in the x prime direction. So this acceleration in the x prime is there. So we have to consider that. It must be there, and we have to consider that because this moves down in the x prime direction, so there is acceleration. So I can rearrange this and say this, that the acceleration, because the question here is asking us about the acceleration, normal force, friction force, I need to redefine this in terms of acceleration. That will help me answer and arrive at a conclusion. So the acceleration in the x prime direction is going to equal to the force of friction kinetic. So I'll put that like this, and that minus the Wx prime, and we take all of this divided by the mass. This right there is an important relationship, and that really tells us everything we need about the acceleration, and that will help us arrive at a conclusion. Even though there's no numbers, we can make up some numbers, and this already tells us a lot about what's going to happen when the friction force goes up here. And that combination of this, which we call the net force, both of these make up the net force in Newton's second law. So we're going to see how that changes as the incline increases and the mass will remain constant. Very important relationship, very important relationship, another very important relationship. Those are the big three we need to arrive at that conclusion. Hold up, I just wanted to let you know I do have a full in-depth preparation course for the 2024 Civil FE exam. If you're looking for an in-depth program that offers you a lot of hands-on practice, where you're going to learn the concepts and tie it with the procedural skills to tackle all kinds of FE exam problems, especially those you will see on exam day, check out the link below. And please feel free to send me all your questions. At this point, we have all the formulas we need to arrive at the right conclusion. But now we're not given numbers. What do? Assume numbers. And I want you to get comfortable with assuming numbers specifically for these types of problems or those problems that give you expressions. We're dealing with these expressions, no numbers. We can assume logical numbers. Let's do that. Here's what we do. So what we'll do first is say we have the inclined plane and another inclined plane that I'm going to increase the angle for this one. So the first inclined plane, I'm going to assume an angle theta of 20 degrees. And here the angle theta will be 30 degrees. Now note, I'm doing that because the question says the angle increases. What happens? What happens to the acceleration? What happens to the friction force? What happens to the normal force? And so on. We're going to get the right conclusion. So that's what we'll do and do the analysis. With that, we have to assume the mass is 1. So that mass idea of 1, we cover a lot in the course. That's a crucial thing that I want you to assume for the main variables. For example, let's say it's a shaft. The radius is going to be 1. Half of the radius is 1 divided by 2. The diameter is 2 times 1 because it's radius plus radius. So with that idea of 1, you can get other variables as well that relate to that. So we're going to say that the mass of the block is 1 kilogram. That's a big factor or big variable that we need, and the angle of the incline, which we increased. Now we will do the analysis. So we're going to do that for each case and see what happens. Let's start with which one? The normal force. Then I can get the friction force, and then I can get the acceleration. Normal force, it says, is weight cosine of theta. So let's do that here. The normal force, we put that in the calculator, and that would be the weight. Note, the weight is mass times gravity. So I'm going to do that on the side, mass times gravity. So the weight in this case, we can use either SI or US units. Here the weight would be a little complicated in US units, would be 1 slug. So let's use the easier SI 1 kilogram. So we just put the 1 kilogram times gravity, which is 9.81, and that will give us weight units of newtons. So that would give us that. So the weight here is going to be 1 times 9.81, which is 9.81, and that would be in newtons. And that's going to be the case for this one, for the weight 9.81, because it's going to be the same weight. No, that's the weight in units of newtons. So here it says the n value is n w cosine of theta. You can plug this in your calculator. You don't necessarily have to write it. So I'll just write it for us. It's w, which is 9.81 newtons, cosine. What's the angle theta? The angle theta is 20 degrees. Now with that, what do you get? You just put that in, 9.81 cosine of 20, and you're going to get 9.218 newtons. So that would be the normal force, weight cosine of theta. Then the friction force. The friction force, you can do the same thing. Friction force is going to equal mu kinetic. Now we have a problem. Here's another problem. This is something I want you to feel comfortable with. Mu kinetic, we don't know. But you can make up numbers. Usually it's in the 0.2, 0.3, 0.5, or you can even assume 1. You can assume 1 for the kinetic, but here I'll try to keep it realistic based on past experience or other examples we do. It's about, let's say, 0.3. Let's just use that. You can use 0.1, 0.2. So what I'll do is put 0.3. Now, what's going to be the normal force? The normal force we already determined when the angle of the incline is 20. So I'm going to just put that here is 9.218 newtons. Close that. Then we get the force of friction. Put that in the calculator, 9.218, and we get 2.765, and that would be in newtons. That's the friction force kinetic. Things are moving in that. Now let's find the acceleration. Now the acceleration in the x prime direction in this case is going to equal to this formula. We have the force of friction, so I put that in there as 2.765 newtons. Now we have this wx prime. This is a very important component. That in terms of w is what? It's going to be w sine of theta, sine of the angle theta, which is this component. It's going to be w sine of the angle theta. So we need that in terms of theta because that's the crucial angle at 20 degrees. So we do this minus w sine of theta. W is 9.81 as we determined, newtons. And then we do sine of the angle theta, which is 20 degrees. And take all of this divided by the mass, which is 1 kilogram. No, we assume that's 1 kilogram in this case, and that would be the mass at the bottom. Now that allows me to find the acceleration in the x, and that would be when we have an angle of 20 degrees. So 2.765 minus 9.81 sine of 20, divide this by 1, and we're going to get a very small acceleration, negative 0.590, and that would be meter per second squared. Units are not that important as long as you keep things consistent here, so you don't have to write that. We just have a value now for the acceleration. It's negative because it moves down the incline. No, we assume going this way is positive. This way is positive. It's actually moving down, so it makes sense why it's negative, why we got a negative answer. We assumed it's positive here when we put it in F equals ma. Because we assumed it's going up, but it's not, it's going to be negative. It actually goes down. So that makes sense with the negative. Now we do the same thing. Same thing for angle of 30. Then we can compare. So what we will do is find the n value. The n value is going to be the 9.81. That would be cosine of the 30. Since I already wrote this, I'm just going to use the calculator. And I want you to get fast doing this and feel comfortable doing this on exam day as well. Through the quizzes we do in the course, the practice exams, you're going to be ready to really solve problems fast with the calculator. 9.81, and you do cosine. What's the angle now? 30. That gives me my normal force. The equation stays the same, so that's going to be 8.496 newtons. Next one, the friction force. What happens to that? Friction force, kinetic. We take 0.3. That's the coefficient we assumed. That's fine. You can assume 1, 0.5, whatever. Then we multiply that times 8.496. What do we get for that? 2.549 newtons. What's acceleration? Acceleration in the x prime direction, we put that friction force first, 2.549 minus 9.81, the weight. Sine should be sine. Now we have 30 degrees. Watch out. The other one was 20. Now it's 30. And we take this divided by 1, and we get negative 2.356 meter per second squared. Comparing this to this, which has a larger acceleration, the one on the right, when the angle theta is 30 degrees compared to 20 degrees, we have a larger acceleration. And that is what we need. And also notice something. The friction force. The friction force is this when the angle is 20, but when we increase the angle to 30, the friction force actually goes down from 2.7 to 2.5 something. It does go down. Now the normal force is high, and that does go down as well, which makes sense because if the normal force goes down, the friction force should go down because the friction force is dependent on the normal force. So in summary, we know that when the acceleration of the block is going to increase, when the angle theta increases, the acceleration of the block does increase. So these two are out. And here the magnitude of the friction force does decrease. It should be 8. The magnitude of the normal force and magnitude of friction force does not remain the same. That is not true. Answer in this should be A. And finally, to finish this off, I want you to visualize this like this. So you have the incline here. Then this incline is going to keep increasing, and you have to imagine that block also on there. Then finally we hit this angle, and that angle will be that 90 degrees there. So what this is saying is as the incline angle increases, as we increase that angle, the acceleration will increase, but the friction force does decrease. The friction force does decrease because that normal force also decreases. And at the end, this is interesting. If you imagine the block here, do we have any friction force in that case? When it's at an angle of 90 degrees, just straight, sitting at the side, no friction force. Because in that case, we have no normal force. There is no contact between the block and the surface because it's directly, strictly perpendicular at an angle of 90 degrees. And that's the case where we have this thing where it's actually just like this. So there's no contact. If I let go of this, it's just going to fall, right? There's no contact there. There is no normal force. Therefore, there is no friction force in that case. In fact, all of the weight here is going to be acceleration. It's going to depend on the acceleration due to gravity in the y direction. So that weight component depends on 9.81, the acceleration due to gravity. And that's the only thing actually acting there. No friction force and no normal force when it's at 90 degrees.